Okay, normally we would want to look at this problem and tackle it by looking at the data booklet where we're looking for the electronegativity values, because we know the greater the electronegativity value, the closer it becomes to becoming an ionic compound. So really we have covalent bonds, which can be broken either into pure covalent bonds or polar covalent bonds, and then we can go to the ionic bonds. Now the covalent bonds, those are the ones that are sharing electrons. We generally think them as nonmetals bonded to nonmetals. And then ionic, those are where we have greatly differing electronegativity values, a 1.8 difference or higher. And again, if we were looking at the data booklet, we could identify these for certain. Those ionic compounds are going to most often be a metal and a nonmetal because they're greatly differing. So we can kind of look at the periodic table, and those form ions and form because of electrostatic forces between them. We can look at where these elements are on the periodic table and use that to help us identify which ones are the furthest away, and those are probably going to be the polar bonds as opposed to the nonpolar bonds, or the pure covalent bonds, in other words. We don't have anything too far apart. We've got carbon and fluorine, we've got carbon with chlorine, we've got silicon with fluorine and silicon with chlorine. So again, they're all relatively close to each other, so we can assume that we're not going to have any of these greatly differing electronegativity values, so no ionic compounds being formed between them. So they're probably all sharing electrons. They're going to be covalently bonded, and so we can try to identify what's going on with them. And we again can't look up in the data booklet what the actual electronegativity values are, but we want to find something that's not too far apart. Oops. We know that the fluorine is the highest electronegativity value on the entire periodic table, so that's probably going to be a big difference between, let's say, carbon and fluorine. So we can probably rule that one out right away. But silicon, being a little bit farther down on the periodic table than carbon, is going to have a slightly greater value, and so should, or lesser value, and should have a bigger difference between the fluorine and the silicon. So that should be our answer. Again, if we could look at the actual periodic table of the electronegativity values, we would see that that would be my greatest value. It's actually well over what an ionic compound would be. So maybe not the best written question in the world, but we're looking at trends, which is what this one is really getting to. So we know electronegativity value increases, as I go across the periodic table, and it decreases as I go down the periodic table, because I have those energy levels in between that are shielding the outer electron. So my nuclear charge is being shared, or effectively less. So my effective nuclear charge is less the further down I go. So we're looking for something with a greater difference that way.